models. What they do is have three different models, B1, A1b, A2 in this case, and these are different decades at which they're predicting global variability. So what we can see is that this is temperature, this is mean temperature. So what you can see is that the B1, which is the best case scenario, gives us a pattern of temperature change which by 2080, 2029, these are 20-year slips, has got us rising somewhere around 3 or 4 degrees, especially in the northern high latitudes. Some areas are relatively lighter, possibly only just getting warmer. This one, all these have potentially limited rising in the southern hemisphere for the period 2011-2013. This is an old diagram, so this was from a previous IPCC report. But what you can see is if you just look, they basically A1b is worse than B1, A2 is really quite significant, where we're talking about rises of 7.5 degrees by the end of the century at high latitudes. That's a lot of change. And you can pick out, at the global level, of course, the spatial variability of where that will be felt worse. And interestingly, you see, why do you think this is so low in the North Atlantic?
Changing Gulf Stream?
Partially.
Melting of Greenland ice sheet.
Melting of ice. So effectively, if you're warming, all these models you see melt ice at high latitudes. And if you remember when we talked about the ocean currents, the only way that water can get out effectively of the high latitudes is down here or down here. So as the warming and the melting, the freshening of this sort of increases. And you still get warming, even by the end of the century, it's still relatively cold. So for instance, if you look at Iceland, southern Iceland and southern southeast Greenland may not warm that much. They may just be kept cool if the water is cooling. Now, if we take something like the closing of the thermohaline circulation, one of the predictions for the future is, will there be so much melting it will cut off the THC and prevent the Gulf Stream from operating? All these models seem to suggest that there will be cooling, but the area of cooling will become less by the end of the century, so the chance of the thermohaline circulation cutting down are limited. If, however, you then run that to 2300 and you continue rising temperatures and effectively you then start removing significant amounts of the Greenland ice sheet, that's when the possibility of a closure of THC comes more into play. So current projections would suggest that we're not going to close the THC down this century, might weaken it a bit, but at some stage, if warming continued and Greenland really did begin to break up significantly, there would be a phase of shutting down or really restricting the THC. And you can see how these models develop those basic things. Again, the thing about it is that these models, these are SRES based, which are all different on who has more population, who has more energy or whatever, but the global patterns are the end product of just the amount of forcing. That's why they've gone to RCP values. We force the global model with a particular level of forcing, irrespective of how we get there. If we actually look at models and observations and we go back over time, these are early predictions of some of the early IPCC, early modelling of the different A1, BA2, B2, B1 CO2 predictions from about 2001 down here. This was what was predicted by the different models in 2001, depending on the scenario. These are the actual CO2 values. So what you can see is that over the last 10-15 years, effectively the CO2 emissions have followed the A1, F1, the really top continued business as usual type of approach. So in fact the modelling that took place and the projections that took place when these SRES were set up, we're on the top of the range. And I think this is a very important point, because we can criticise the modelling, we can criticise all levels, but if you just look at the SRES, you can criticise them for saying, well, they don't make sense, they're so complicated. But the reality of it is, if you use that sort of approach and you look at your range, we are currently at the top range for predictions of those models when they were first set up, those scenarios when they were first set up. And we are way above B2. We're a gigaton, we're almost 1.5 gigatons of carbon per year ahead of any adaptive strategy that we might have been actually looking at. And if we look where it comes from, it's not surprising. This is from this CO2 Now site, which is a little bit partial, shall we say, in its approach, but effectively 91% of CO2 comes from fossil fuels and cement, and 9% from land use change. That's not going to change. I mean, we're not changing where we actually get it from. These are so in terms of what forces the model, if CO2 is the main gas that forces the model, this is where the CO2 comes from, then those are the things that's going to drive. And whatever drives fossil fuel use will drive that, is the figures from 2010. Yeah, they're in, and there's good, the data are in Nature Geoscience in 2010. Query it out. Models have uncertainty. We know that we have physical uncertainty in the physical processes. We have uncertainty in the statistical elements of any modelling. And we've already seen that because we use different scenarios, there's obviously uncertainty as to which scenario is likely. It is a very complex problem. And each model's different. Each model parameterizes in different ways. So that adds uncertainty, apart from the uncertainty that obviously exists in the model itself. So the current approach is to tend to use a whole range of different models forced by these same scenarios, and then looking at the output. So if we look at global surface warming projected by models between 2000 and 2100, and we look at the range A2, A1B, B1 in particular. Those are the key ones. You see A2's right at the top, A1B. It takes over from A1B, so A1B up until the middle of the century is the worst case scenario, and then we have the blue is the B1. The one down here is the constant composition commitment. So whatever happens, if we cut everything off, we've still got that commitment in the gas. Effectively, what the IPCC have done is say, right, for those running those particular models, we've got a different number of models. So we have 17 models that ran with A2, 21 models that ran with A1B, 21 with B1, and 16 that worked out. So, and then what this uncertainty is the variation between the models. So that's the uncertainty. It's the range of the projection with the different model, and it's all there. It's saying, right, now out of 21 models, this was the central value, and this is the top value that was predicted, this is the low value that was predicted. This provides an interesting philosophical point as to which one, you're a policymaker, which output do you go on? The safe output for a policymaker is to take the average. You say, oh, we've run 21 models, the average value's 2.5 degrees, let's go with that. And that's the sort of way most people would look at it. The reality, of course, is that in terms of probability, if one model is so much better than the others, then that's the one you should go for. But evaluating how one model is better than another is very difficult. But it may well be that actually the model that predicted the top end of this is a better model because of what it parameterizes and how it does it. But that's not, you don't do that. I mean, well, Angela Merkel could probably get away with, doing that from a sort of relatively renewable base and say, I'm taking that, and she could sell that to the German public. Cameron trying to get UKIP votes would have absolutely no chance at all of taking that. You know, as far as UKIP, non-climate science believing end of the voting spectrum is concerned, all these are theoretical anyway, and why not take this one, which is far less? Or why not take this one, because it's the lowest? It's a political decision. So again, coming back to the point, the science is there, the science has uncertainty within it, the social science has uncertainty within it. When it comes to converting that knowledge into policy, it's a political issue. Selling it to the voters, selling it to the... And what we'll see by the next election here is, as you've seen, is a pulling away from renewable energy. A real pulling away from renewable energy, a reinvestment in nuclear, a commitment to fracking. That's an interesting one because actually a lot of the fracking sites are Tory seats and they don't want to be fracked. But the Conservative government knows that fracking will provide a cheaper, safer in terms of security, energy security source. Therefore, the fracking debate is a difficult one too, but it's very easy to go against wind farms, especially onshore wind farms and solar farms that cover fields. You know, if you covered Sussex with solar farms, you'd lose half of the Sussex vote. And UKIP, if you look at the UKIP proposal, UKIP is clearly against renewable, anything that is sort of renewable rather than necessarily sort of fossil fuel based. There's a scepticism about that. And if you look at where the election is going to be fought, especially the general election, not the European election, energy policy will be there because effectively you'll be looking for energy which is cheap rather than necessarily environmentally greenhouse gas friendly. Because it's energy prices that's the issue, not where and how that energy comes from, or the security of that energy. So we can see that, you know, the way a graph like this could be used by different politicians or policymakers would be very, very different indeed, the way they would see it.